Well, be careful to do a good job then.
Yeah, so it's my pleasure this morning to introduce Dr. Kent Weigel. Kent is our department chairman here in the Department of Dairy Science. He's also our extension specialist in dairy cattle genetics. And I asked Kent to go ahead and make a presentation this morning, so I'll turn it over to you, Kent.
Thanks, Paul. What I'd like to do over the next half hour or so is talk about our big project on genetic or genomic selection and feed efficiency. Can everybody hear me all right, or should I go with the handset instead of the speaker? Okay?
I can hear you fine, Kent.
Coming through fine.
So this project started about 4 years ago. It was funded by the USDA National Institute of Food and Agriculture, and it involves a number of different individuals at different universities, as shown there on that first sheet or first page. Mike Vandehar at Michigan State is the overall project leader. Lou Armentano and I are Wisconsin part. A number of different people involved. The objectives are there. Some of you a little bit of this, so I'm not going to go through great detail, but the big one is develop this database of 8,000 cows with feed efficiency data and genomic test results. The genomic test results part is easy. You can go out and test cows and be done with that in a few minutes. Measuring them for feed intake or feed efficiency is the difficult part, and that's why this hasn't been done before. 8,000, I'll mention this later on, that gets you a long ways in terms of reliability and of genetic predictions, but it's just a step. 10,000 is better, 20,000 is better. The number keeps going up, so every time you collect data on 1,000 more cows, somebody publishes a paper that says you need 5,000 more. So we're trying to do our best. A little bit about the genetic architecture of feed efficiency. Number 3 is really important. Try to implement genomic selection programs for efficiency, and that's really be the focus of the next year or so, to develop some preliminary predictions for young bulls and so on. Sport schools, number 4 has got Victor's name all over it. That relates to nutritional grouping particularly. And Michelle Watio and some others are working on 5. Lists all the people there below. The main 2 are Wisconsin and Michigan State. Florida, Iowa State involved, and several others. What I did on the next pages is I just pulled the abstracts and a few of the tables for 5 papers that have been published so far this year. There's actually a 6th that I forgot because I'm not a co-author on it. That one's from Michigan State, and it looks at, I'm going to mention it now so I don't forget to come back to it. It's Potts is the lead author, and working with Mike Allen and Mike Vandehar and Adam Locke, and that looked at the repeatability of residual feed intake for cows on high and low starch diets. So basically they took a bunch of cows, measured them for feed intake and feed efficiency on high starch diet, and then switched them to low starch or vice versa, and they actually found that within the same lactation the results held up reasonably well, which is a good thing because you don't want efficiency of a cow to depend. I mean, it is going to depend on the diet, obviously, but you don't want on one diet these cows are efficient, and then it's completely the opposite if you change the diet a little bit. That would be bad. So to just go through these studies, I'm going to try and pick out just a few key points of each. Some of them are pretty interesting and of practical value. Some are a little more theoretical and may not be good for a lot except bedtime reading material if you need some sleep. But I'll start with Lydia Hardy. She did her master's with me and then moved on to Iowa State for a PhD and still working on the same project but at a different location. And what she did, and I wanted to talk about this one first, is take data from a bunch of our experiments here in UW, Madison, and Dairy Forage, and show or put those together into feed efficiency database. And then the article talks a little bit about that. and I want to show a little bit about what's involved, just to give you a background of how this project really works. And so I'll go ahead to the next slides there with table 1. And so what you might imagine is we just decide, okay, today we're going to fit one, all agree upon one diet, and then everybody at all these different stations is going to start measuring feed efficiency on cows, and when we get to 8,000, we quit. If it were that simple, that would be nice. The reality is you can't just take over the facilities for 5 years and say nobody else gets to do any work on this farm because we're taking all the cows and all the feed efficiency gates or whatever. And the other piece of that is we could actually go back and retrospectively bring in some studies, and there was a lot of work doing that. The only reason it actually worked in practice is because Sandy Burdix is the lab technician or lab manager for the nutrition group, and she had all this stuff archived in her files and in her brain. So we were able to go back and get a lot of studies where we had DNA available. But just as an example, Lydia put 13 trials up there that she had in this study, and you can see, well, there was actually one from Cargill in there. There were 4 of them at Dairy Forage. There were a couple going, at least one going back to our tie stall, or 2 our tie stall operations for the New Arlington facility, and then there are several with our Incentech system at Arlington. So you've got animals that are recorded in tie stalls, they're recorded in the Incentech system. We've got Kalen Gates at the Virginia Tech and Iowa State. Michigan State is doing tie stall annual way back. They got GrowSafe at Florida. You got different systems, got different types of studies where some are continuous studies where the cows stay on the same diet full time. We got some that are Latin square where the cow starts on diet A and then moves to B and diet C, and the next cow goes diet B and C and A.
Have you met Mary? Yeah. Oh, okay, okay.
Yeah, he survived.
So different cohort is who got the same diet. So you see it could be just one cohort where everybody's on the same diet, or up to 10 different diets on an experiment, and so on. And so in this study, there were 13 experiments, 46 cohorts, and 677 animals. And then in the figure 1 below, it kind of shows the stage in lactation, different trials, and you can see that what we focused on in this study is data between 50 and 200 days, and the idea was to get at least 6 weeks or so of data per cow. And some studies start earlier, some go on later, but the goal was to have a period in the middle where everybody had data, and we more or less achieved that. And the idea is, well, a couple things. First is during this period is around peak lactation, so that's when the majority of milk is being produced and feed's being consumed, but also to try and find a point where cows are more or less stable in terms of not losing body weight and body condition rapidly, or not gaining weight and condition rapidly, not having large effects of pregnancy. So that period in there between like 50 and 200 is a little more stable. You get a little more variable results if you go right around lactation or that sort of thing. Table 2 on the next, on the right side there, summarizes our data. Some of this might be interesting to you who know more about nutrition than I do, but it summarizes the data from these studies. So, for example, our first lactation cows, body weight, 595 kilos, 691 for the second and older lactation cows. You can see some real beasts in there. The range was 480 to 963 kilos. So that's a big cow. Dry matter intake in kilos, about 22.5 for first, 27.3 for laters. And then if you go down to the next few, the total energy intake, for example, for the first lactation cows, 35.9 megacals. Of that, 24.3 for milk energy, over 2 for body weight change, and about 9.5 for maintenance. And then you can see for the older cows, taking in about 43 megacals a day, about 3/4, a little under 3/4 of that for milk, about 11 for maintenance, and not as much as the younger cows for body weight change because they're not growing anymore. Their energy output and energy input is relatively similar. They're not creating energy nor making it disappear. And then the energy density of the diets. And one of the things that in the dry days of milk, one of the things, if you see the little histogram here, figure 4 below that, that was kind of clever that, you know, you guys might not realize this after all these years, but Shaver is a clever guy. And Shaver, Randy figured out that why don't you just calculate the realized energy density on each of these trials or each cohort as the total energy in and the total energy out, basically, where energy out is either milk or body weight maintenance or body weight change. And you can calculate the energy density of these diets. The alternative is to go to the feed ingredients and the NRC and to what the energy density should be. And Lydia actually did that in the bottom graph there, or went back to these studies, some of the studies at least that were published in the literature, and looked at the published energy density, which is what came from the ration formulation, and then the actual realized energy density. So one is what you fed the cows, and the other is what the cows got from it, basically. They don't always agree. In some cases, they're very close. In some cases, somewhat different. But the realized energy density in megacals per kilo went from about 1.4 up to about 1.75. And so there are different ways to think about feed efficiency. One of them that I think is kind of interesting, but tricky to interpret at the same time, is what is the energy density that this cow can derive from this specific diet. You know, there are other measures that are harder to interpret, you know, harder to explain. I think that one has some appeal, maybe only to me as a geneticist. But you see, there's some variation in the diets, but we're not feeding anything crazy. There was one study, for example, that Armentano had a lot. It was an oil feeding study, different kind of oils in the diet, and that one was a little different. But for the most part, they're sort of within the range of standard diets that you see out there. So that one of Lydia gives you a little background. There was another paper here by one of my students, Chen Yao, who's a PhD student now. This was part of her master's, and I'm not going to go through all the graphs and tables from it. The point of it was that what she did in that paper there, that short communication, was to take SNP data from the genomic testing and combine it with the health history. And it would be very much like in human medicine to calculate the relative risk of a certain disease. So you say, okay, do you drink, do you smoke, how old are you, where do you live, blah, 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 and then combine it with the genetic testing information to predict risk of heart disease or that, right? She did this with cattle data in our herd, and it was a relatively small number of records, so I'm not going to spend any time on the results, but the point is that it does matter, okay? And so when we look at these sorts of things, you know, we geneticists particularly always think about, oh, we do the DNA test, now we know which calves to keep and which calves to sell. And we always really, I think, have to think about it in like a decision tree of, okay, is this animal good or poor on her genomic test results, and then also, you know, does she have a clean health history, or does she have respiratory disease? And you know, that group of animals that, you know, that have a checkered past in terms of health industry and a poor genomic test are the ones that need to perhaps find a new home, and the others are the ones to keep as replacement heifers. And that's obvious on one hand, but people forget about it sometimes too. The next one I'm going to spend a little more time on. This is lead author is Rob Templeman. He was actually an office mate here in Madison of mine during grad school, during his PhD, and he's at Michigan State now, has been for some years. And this is the first big summary of the data. There's a lot in that paper about energy sinks and partial regression coefficients at each location and so on, of body weight change and maintenance and milk energy by diet. I'm not going to get into all those gory details, but he does present sort of the first heritability estimates, some of that sort of stuff. I wanted to at least show you those. Table in the upper left here, table 1, shows the source of the data. So you've got in the U.S., Florida, Iowa State, Michigan State, Dairy Forage Research Center, and then us at UW, and then the USDA Beltsville facility, AGIL. You've got 4 research farms in the Netherlands, and then 2 in the United Kingdom. The 2 in the UK are a bit older data, and we also had some issues with the data from Lang Hill because they do grazing research there, and we had some issues early on where they say here are the intakes for these animals, and that's the total intake. We recorded everything, and then we look at the milk energy output, and we look at the intake, and they're creating milk from nothing during some parts of the lactation. And we said, go back and check your grazing records, and they said, oh yeah, we had some cows on grass for a while, and we didn't tell you about that. So magical cows that can create milk from nothing would be valuable, but so far not real. So even in Scotland, they don't have those. So see the total number of records of cows there, 4,893. So this analysis was done about close to a year ago by the time you account for review and then publication. So we're probably up over 6,000 now, getting close to the 8,000. Hopefully we'll get there. We should be close. We'll certainly be over 8,000 lactation records. Some cows get measured more than once. And the limiting factors at places like Iowa State, for example, they've measured everybody, and the only thing you can do is wait for more new cows to calve. In our situation, we're limited by the number of cows that fit in the Incentec pen, and we'll have some we haven't measured. We're trying to get everybody. 90,000 weeks on test, average 13 weeks per cow, but it varies a lot from one place to another. And then this crazy-looking graph below shows heritability during the lactation. I wouldn't spend a whole lot of time worrying about that, but the United States are the diamonds. So you sort of see in mid-lactation, around peak lactation, about 14 or 15% heritability. At the ends of the tails of these lines, at each end, it gets kind of variable. Especially, for example, in our data, we weren't measuring cows before 50 days or after 200. So as you get toward those values, the number of animals was quite low. But overall, the heritability is about 15% visual feed intake. So it's less than the heritability of dry matter intake, which is up in the 30s. Heritability of milk production is up around there as well, around 30%. The heritability of body size is 40%, maybe a little more. But this is the heritability of dry matter intake after you take away or subtract off the energy for milk output, for body weight gain or loss, and then for body weight maintenance. Okay. And then the next one, I just put that up there to kind of remind me to mention this repeatability issue. So the top set of solid lines there is the repeatability within lactation. And so, for example, in that study of with Adam Locke and Van de Haar and Allen, where they looked at changing the diet and then seeing how that affects efficiency, they were saying, oh yes, well, feed efficiency or residual feed intake is repeatable, and you go from one diet to the next. That's within the lactation. and the repeatability between lactations is much, much less. And, you know, that's kind of a concern. The other side of that that makes me not worry quite so much is not that many animals were measured in 2 times in multiple different lactations, but your heritability can't be any higher than that. So if the repeatability between lactations is 25 or 30%, heritability of 15% is catching most of that. There are other things, maybe half-hood pneumonia, for example, could affect performance of an animal throughout its life and so on. But a lot of these things it's much more repeatable within lactation, I guess. Next study is one of those I would say don't spend a lot of your time on it, but I put it in there just to show you that we're really busy and we're doing lots of stuff. It's a little more theoretical. It's by one of Rob Templeman's students at Michigan State, Yongfang Liu, and she looked at an alternative way of handling or measuring efficiency. So residual feed intake, what you're doing, as I said earlier, is you're taking dry matter intake of the animal, you're subtracting off the energy for milk, the energy for maintenance, the energy for body weight change, and then you get a leftover part, and that leftover part is what you call residual feed intake, and if it's high, then you say, well, that cow's eating more than she needs, she's inefficient, and if it's negative, then you say, well, she's efficient, she's eating less than she needs. But the fact that it's sort of a leftover from a statistical model leaves us all feeling kind of a little icky, and we say, boy, there might be other stuff in there too. What if my model's wrong? Then, well, my feed intakes aren't going to be what I think they are. And the other piece of that I won't get into today, but what exactly is that leftover residual feed intake piece? Well, we know part of it is differences in digestive efficiency, part of it is heat loss, part of it is activity. Basically, it's all the things that could burn energy that we aren't measuring, okay? And we're assuming when we say we want negative or low values that those extra things that are burning energy are not useful, okay? What if some of those extra things that are burning energy are useful? So, for example, what if, how much energy is required for sort of immune function? People ask that question. Well, I don't know that, but that's part of residual feed intake. So we would want to make sure that if you're selecting animals that are low or negative RFIs, that aren't selecting animals that are more likely to come to infectious or metabolic disease, for example. So there's a bit of a black box piece that people aren't comfortable with. And so what this student decided to do is look at a different approach, where she looked at, for example, dry matter intake, and then dry matter intake adjusted for milk yield, and then dry matter intake adjusted for milk yield and maintenance, and sort of a stepwise approach. The heritabilities were very similar, about 14 to 16%. Repeatabilities, about 60%. There's again, sort of within and between lactation piece of that I won't get into again. But you see the estimated breeding values were almost identical correlation. So not much is gained by a new approach to the same underlying data. And then the international piece I'll mention here. So Yvette de Haas is at Wageningen University in the Netherlands. There's a whole bunch of other people listed here. And this is called the Global DMI Project, Global Dry Matter Intake. And this came about at the same time that we started our project. And so we did participate in a limited way. We don't want to just send all our data away and have these folks publish it and become the U.S. branch of the data collection monkeys for the Global Dry Matter Project. But we put it out there, and I think from Wisconsin we sent data on about 500 records from 450 cows. Diane Spurlock at Iowa State sent in about 400 cows to participate in this. And so they in total had 8,700 animals, about 12,000 lactations. Now, some of those animals were not milking cows; they were heifers, about 1,700 or 1,800 heifers about 7,000 milking cows. There's a couple studies from Australia that show a relationship between feed efficiency as a growing heifer and as a lactating cow. It's not zero, but it's the correlation. It's fairly weak. It's stronger between as a heifer and as first lactation, and as the cow gets older, the correlation goes down even more because she's not really growing anymore. But you know, the heifers do use feed too, so it's important to maybe measure their feed efficiency. So I wanted you to kind of be aware of that. You can also get some statistics about dry matter intake of cows in the different countries in these experiments. So the Wisconsin cows get the prize for eating 25 kilos of dry, 25.1 kilos of dry matter a day, just slightly more, I think, than the Iowa cows, and then everybody else sort of followed behind. And now, sort of moving on, I guess I mentioned the study of Michigan State also that I didn't give you. There's one more paper that will be coming out later this year. Well, probably more than one, but one that I've been closely involved with, and that involves genetic and phenotypic correlations between these feed intake traits and type traits. So when we started this project, we really didn't want to spend a whole lot of time going down that road. We decided let's focus on measuring body weights, and then the Holstein Association came and said, well, you know, you should classify these cows, and so we can look at relationship between our linear type traits and feed efficiency. And we said, no, that's fine, no thanks. And then they came back again and said, how about we classify them for you for free? And we said, sure, okay. And so they did classify a couple thousand cows at the various sites. And in the Netherlands, they did the same thing. So there's a student in the Netherlands, she's actually a Mexican student in the Netherlands, who's looking at the relationship between type traits and feed efficiency in both countries. And so that'll come out a little bit later this year. It's not surprising, I guess. Big cows eat more. Big cows are less efficient. But I wanted to show this table here on the left, the one with the green and the yellow, came from Mike Vandehar at Michigan State, and the definitions are up on top. In this case, he's looking at gross efficiency, so the energy devoted to milk body tissue divided by the total energy intake. And so if you look down below on the diagonal, you have the heritability. So 39% heritability of milk energy, 51% heritability of metabolic body weight, dry matter intake 41%, gross efficiency about 12%. And remind you, metabolic body weight is body weight raised to the 0.75 power, which is kind of a biological standard way of doing it. And so if you look above the line here, these are the questions we're getting, this body size issue, and I think that it's confusing, and I'm not sure at this point if we're helping the confusion or adding to it. We're trying to help it, but I'll talk about that a little more in the next slide. This 0.10 is the correlation between metabolic body weight and milk energy, so milk production basically, after adjusting for fat and protein content. So when you hear that people say big cows give more milk, well, do they or not? Well, the genetic correlation is 0.10 with a standard error of 0.06. So is it a positive relationship? Well, yes. Is it statistically significant? No. Sort of marginally approaching significance. But, you know, a 0.1 correlation is damn near zero, and quite frankly. And so there's a very weak relationship between body size and milk yield. And this argument that I need big cows to get more milk is simply not true. Milk energy and dry matter intake, 0.7. That's not a surprise. Milk energy and gross efficiency, 0.65. Also not a surprise. Dry matter intake with metabolic body weight, 0.48. Big cows eat more. They eat a lot more. And then this metabolic body weight with gross efficiency minus 0.3. So clearly, the larger cows are less efficient, and dry matter intake and gross efficiency actually are almost no correlation. And so what do we take from this? Well, there are two different ways to increase efficiency, right? So milk energy and gross efficiency, 0.65 correlation. So more milk, cows get more milk, cows are more efficient. Cows that are smaller are more efficient. Next slide here, Vandehar goes through some calculations and shows, well, cows of different size, either make them smaller at the same amount of milk yield, or you can keep them the same size, get more milk. You actually get greater returns by getting more milk from the same size cow than you do from shrinking the cow, and that's kind of what's shown here. And that's, I think, where now the message is getting murky, because people are saying, oh, well, gee, I'm still better off going for more milk than going for smaller cows, so I'll just go for more milk from big cows. Well, he's not saying that. He's saying more milk from the same size cow, and it's getting interpreted a little bit awkwardly. But yeah, increasing milk yield does increase your profit more quickly than trying to shrink the cow. Cows certainly shouldn't get bigger for a lot of reasons, including facilities and other stuff. And this also depends a little bit. I mean, as milk and feed prices change, of course, that would affect things too. At the bottom, I threw this in there because this came as part of an email discussion with Randy Shaver and Lou Armentano and Mark Bogus, the director of Dairy Forage Center. This was in Progressive Dairyman last month. Basically, what does it take to get a 100-pound herd? What's the secret to success? Well, secret number 7, you need big cows. And that's the sort of thing that we're fighting out in the field. I think this person's a veterinarian, I'm not sure. But basically people saying, wow, if you want a lot of milk, you have to have big cows. There are a couple things here. Now, the last sentence that says when elite production is the goal is pretty important. I don't think elite production is the goal. I think profit's the goal. But the piece before that is really troubling. Large cows have proportionally lower maintenance costs. The way maintenance costs are calculated by metabolic body weight, that's not possible because they're proportional to body size. So as the cow gets bigger, her maintenance costs don't diminish. Maybe they're thinking of fixed costs or something like that. But there's a lot of confusion out there, and people aren't helping us in general by doing this. What else? The genetic trend here in body size in U.S. Holsteins, I put this together for a proposal we just submitted. It's increasing at an increasing rate, so exponentially, because with genomic selection we can make faster progress, which means if we have bad habits like fetishes with large cows, we can satisfy those more quickly. And cows, actually, Holsteins have increased by 1.5 genetic standard deviations in the past decade, which is a huge amount. I think it's second only to progress for protein yield. We're making cows bigger, and we're doing it at an increasing rate. Okay. The next slide I put in came from Jude Capper's stuff at Washington State. Looks at Holstein and Jersey. It actually looks at the energy per unit of cheese produced, Holstein and Jersey. And I wanted to put that in there to remind me to tell you that we are working. We have a big $4 million grant submitted to USDA, National Institute of Food and Agriculture, that will, if it's funded, will get us really into a lot of Jersey research in a hurry and probably lead to 200 or 300 jerseys at either or some combination of Arlington, Prairie du Sac, Dairy Forage Farm, and Marshfield. If that gets funded, we'll be bringing in jerseys in large numbers very quickly. If it doesn't get funded, we're still going to do it. Jerseys are now, I learned last week, 13% of the inseminations in the U.S. last year, artificial inseminations, were to Jersey. Jerseys have higher fertility, so Actually, proportionally would be a higher number than that, the number of pregnancies. So 13% of the semen sold was jerseys, and a higher proportion of that jersey semen is sex semen. So the rate at which jerseys are increasing in number is pretty remarkable, and we need to be doing some jersey work, because the idea that these are just little brown Holsteins, which is how they're fed and managed, is not accurate. And then the last slide, I just wanted to put this in there to remind people that genetics is nice. I think it's cool, but there are other ways to increase efficiency. And so the Van de Haar put together that basically shows in terms of whole farm energy efficiency, 21% is kind of typical, 28% protein efficiency. You can increase production, and that helps you in both energy and protein efficiency. You can increase longevity, or at least the opportunity for longevity if the cows are good and you want to keep them. You can reduce age at first calving. You can shorten your calving interval. All that sort of helps. You can do grouping. That was the point of this table. So by grouping, for example, you can increase protein efficiency pretty remarkably. But the last line, feed waste. So the whole, what happens to that feed before the cow eats it is huge, and spend a lot of time on genomic selection for feed efficiency while letting feed spoil is a really bad plan. So that was kind of where I wanted to stop, just to put it in perspective. So I went maybe a little long for questions. Paul, are you still with us?